Okay, welcome everyone. We have a busy schedule of 4 speakers today. We will not mention the ITC lunch, the ITC colloquium that took place. So let me just read off all the presenters at lunch today. We will start with Adam Lanman from MIT, not far away, who will tell us about constraining intragroup media and localizing fast radio bursts. And after that, we'll hear from Hina Suzuki from the University of Arizona. Where is Hina? Oh, over there. About the high-order photon rings around Kerr naked singularities. Okay, that should be interesting. We have never seen a naked singularity, but maybe we will. And then Catherine Petretti from a student in our astronomy department. Where is she? Catherine, over there. She will tell us about constraining dark matter isocurvature fluctuations with the microwave background. And finally, we'll hear from Pranav Sanghavi, also from here. Pranav is here, talking about building and commissioning the Coherent all-sky monitor, a new radio telescope to probe the local universe using fast radio bursts. So we have 2 talks about FRBs today. We'll start with Adam.
Okay. Can you all hear me? Did you switch it on?
I don't. No.
All right. There it goes.
Oh, okay. I'll try to speak into it then. All right. Yes, thank you for having me, and thanks, Scott, for the invitation as well. My name is Adam Lanman. I'm a postdoc at MIT, and today I'm going to talk about a recent results that are coming out of the CHIME FRB experiments with studying galaxy groups using FRBs. So for just sort of a lightning overview, FRBs are extremely bright, extremely brief flashes of radio emission with spectra that show this characteristically large dispersion, where the signal at lower frequencies arrives later than the signal at higher frequencies, and the dispersive sweep is proportional or set by the column density of free electrons along the line of sight. And so the first FRB ever discovered is this Lorimer burst shown on the right, and that's the dispersed signal. So the large, among other clues, the large DMs of FRBs indicate that these are of extragalactic origin, and that so we can use, if we know the galaxy of origin of the FRB, we can study the structure in front of it and use that total DM as a way to constrain the contents of those intervening structures. So we see contributions from the host ISM, the host circumgalactic medium. In this case, I'll be talking about galaxy groups, so as well intercluster media, and then from our own galaxy and our own Milky Way halo. So the FRBs I'll talk about today, or really just the one I'll talk about today, was discovered by the Canadian Hydrogen Intensity Mapping Experiment, which is these 4 cylindrical dishes, each with 256 dual polarization feeds. It's located in British Columbia, and it's currently the most powerful FRB detector in the world, although I'm sure DSA will soon blow us out of the water. Averages around 3 FRBs per day, or roughly 1,000 per year. In order to successfully localize FRBs, we have a network of outrigger dishes spread across North America, each of which carries a buffer of raw baseband data, and when it receives a trigger from CHIME of an FRB candidate, it will write that data out to disk, and then offline we can beamform those outrigger signals and cross-correlate to VLBI. So with the full array, we can achieve, with our systematics, roughly tens of milli-arc seconds localization. But with the first outrigger, which I'll be talking about today, well, the one up there, is we can, thank you. Thank you, which we can achieve arc second localization, which is sufficient for host galaxy identification. So last year, we published a catalog of our first VLBI localizations using this outrigger. So that was 81 localizations, and of these, we got 21 secure host galaxy detections. And I'll include this QR code at the end of this talk as well. So these are the 21 host galaxies from our so-called gold sample that were the most confident associations. They're mostly spiral, a couple elliptical. There's at least one double galaxy system. And a full analysis of this is still forthcoming. So the rest of my talk will focus on this source right here, going from roughly 0.2 redshifts. And there's a lot of interesting things happening with this one. So the host galaxy happens to be a member of this massive group, WH24, which I've shortened to WH24 J1218. In the foreground of it, there is this other group, NSCS J1218. And then in the foreground of that, so showing a zoom out over here, there's a Tully group. And these are all in roughly the ballpark of 10 to the 13 solar masses. In addition, that second group along the sight line falls at the intersection, sorry, the colors don't quite work in on the screen, of these two galaxy filaments. So the colors here are mapping member galaxies to each filament. And on the left, we have a sort of a face-on view, and then a side view over here showing the sight line as it passes through this foreground group and the associated structure. So there's a lot going on here. So our goal is to take the best available data for each of these groups along the sight line, along with sufficiently well-motivated models of the density profile, and come up with estimates of the DM contribution from each halo. So I have three models that I'm considering. There's this modified NFW profile, which is commonly used to describe the DM contributions from CGMs of galaxies. And then there are these two profiles derived from this universal pressure profile, which is an empirical model fit to more massive clusters. So for sort of spanning the range of models commonly used to describe these halos. And then on the right, I have a diagram showing the coordinate system used for the integration. So each model is taken to be proportional to this parameter FG, which describes the fraction of baryons, or fraction of mass in the halo that is in a gaseous state and able to contribute to the DM. The common lore is that the halos will form with the universal baryon fraction, omega b over omega m, and then due to feedback effects in the member galaxies, some of that material will be pushed back out. And as a result of groups and single galaxies having shallower potential wells, they will have a lower gas fraction than more massive clusters. And that's described well by this plot from a recent Papeso et al. Paper showing how with less massive clusters, this FG parameter is much lower. So by comparing the observed DMs to the model DMs, we can set a very conservative upper bound on this gas fraction. So we say that the total DM is proportional to this integrated model and this parameter. And we've normalized the model to some, so that the total gas fraction at the virial radius is the cosmic fraction. Just call that DM bar. And then if we take, we can subtract off estimates for the large-scale structure and for the host galaxy and come up with an upper limit on the gas fraction there, or get the value of the gas fraction. But if we just pretend that there's no large-scale structure and no contribution in the host galaxy, then we just set it as an upper limit. There's a lot of uncertainty in modeling these galaxies, or these halos. So I've done a Monte Carlo analysis sampling over the uncertainties in the masses and the concentration parameters. And in the case of the host group, there's also uncertainty of how deep into the halo the host galaxy is. So there's an additional sampling over the line of sight depth. And for these DM histograms, I'm assuming the gas fraction is 1, which is, of course, not a good assumption. But the vertical green lines here are showing the total available DM for this FRB against each individual halo's DM estimates. And we can see that they're clearly, especially this middle one, well exceeding what's available. So combining the contributions from the 3 separate halos, we have the total halo DM of all the foregrounds, and again, the total DM budget. This is what's available, and then if we subtract off a Milky Way contribution. And then these are the 1 sigma lower bounds for each. So each curve is a different model. And then taking the ratios of these lower bounds on the DM halos and the upper bounds on the extragalactic DM available, we can set these upper limits on the gas fraction. And then we do that integrating out to different maximum radii. So one here is for one R500, one definition of the virial radius, and then R200 and RV being differently motivated virial model or spherical collapse model. We can set these upper limits, and then comparing with the gas fraction estimates from that Papesso paper and also an earlier estimate from Eckert, we find that these upper bounds are pretty consistent with Papesso at R500, but slightly in tension with Eckert, bearing in mind that these are very conservative upper bounds, at least for the two ICM models derived from higher mass halos. If we consider the modified NFW model, then everything is consistent. Yeah, and that's pretty much all I wanted to talk about. So this is the KK only catalog, that first outrigger. These three, well, I didn't talk about the other two, but there were 3 FRB sightlines passing through groups and clusters. And from the sightline, we're able to set some loose constraints on the gas fraction. And in the near future, you can expect the catalog from the first 2 outriggers to come out. So thank you.
So Adam, there are 2 other probes. Can you tell us if they are difficult to come by? One is X-rays, obviously, and that has a different dependence on distance. And the second is 21 centimeter absorption. Are these not doable? I mean, is it not practical to get information from those 2?
So you mean X-rays as a separate measure of the?
Yeah, of the actually X-rays are proportional to the square of the density. So that's a different measure of the same profile.
No, certainly. And the groups in this sample, none of them were detected in X-rays. So I suspect if you went and did a deeper search, maybe you'd find some X-ray emission. But sorry? No, nothing detected in Rosat. And it's also, unfortunately, in the wrong side of the sky for E Rosita. So.
How about 21 centimeters?
I hadn't considered 21 centimeter. But I guess 21 centimeter would be a neutral phase, so we wouldn't find
the neutral component, there is always neutral component because there is a combination within the gas, right, in any environment. So the question is whether you can detect that signal. Because you are doing it in the radio. Anyway.
Well, I guess this is more analogous to an absorption signal, because it's well, I know it's not literally absorption.
The 21 centimeter gives you also the redshift of where the absorption takes place. If you see absorption in 21 centimeter.
Do you expect strong 21 centimeter emission from the intergroup?
Absorption, just like, because the source has a high surface brightness temperature, so it will be only absorbed by the gas that has a lower spin temperature.
Okay.
It's very, very hard to get the columns to see this, to get the redshift to the FRB.
Did you check the numbers?
Yeah. I mean,
Did anyone search?
Oh, so you're asking about the host galaxy redshift from?
No. But the point is, you are observing in the radio. Just go to the frequency of a 21 centimeter
right
line, and then 1.4 gigahertz redshifted, and see if you have absorption there.
Well, certainly. So I did at one point look into this for Chime specifically with to get the 21 centimeter line into our bands 400 800 requires a higher redshift, and that increases the dispersive sweep. And our baseband buffers are limited in size, so we actually lose the top of the bands just at the point where the 21 centimeter signal would enter our band. So I think with Chord coming online, we won't have this cutoff anymore, so that may be an option, but it's still also you're looking for a single feature in this large spectrum, and it's already pretty faint, so.
Well, I was just going to say, Chime was built for cosmology between redshift 0.8 and 2.5. So the top of the band, you're already at redshift 0.8. This cluster's at 0.11.
Okay. Any other questions to Adam? Comments? Let's thank Adam again. Thank you.
Inside the house. It's our change.
All right. Do you hear me okay? All right. I'll just set it here. Start. All right, thank you for everyone for joining today. I'm Hina Suzuki from the University of Arizona. I just finished undergraduate there in astronomy and minor in electrical computer engineering. Today I'm gonna be talking about high-order photon rings around Kerr-naked singularities. The core question is simple. If we push the VLVI observations in further higher resolution, can we really detect event horizon, and then can we distinguish those with the non-horizonless object forming the similar image? So this is the image from the EHD collaboration here of the center of Sagittarius star. At the current resolution, we see a bright ring with the black shadow in the middle, but the image alone does not directly observe an event horizon. And the real question is this black hole or is this something else? This could be mimicked in a different compact object that has been discussed in EHD papers in Sagittarius star. So there's multiple objects that could, especially these ones, it's not working, could mimic the black hole in resolution. We have a compact object in the center and have a orange donut showing up in the image. So a little bit of a background of what we are talking about. Photon rings are photons made of photons that went orbit around the black hole or a compact object multiple times before escaping to the observer that we observe. And shadow is what we are talking about. Shadow is in this black region, and then photon rings are made of multiple different rings that has been labeled by how many half turns that they went around black hole or compact object. And if you look at photon rings in VLVI observations, this is what you will observe. This visibility amplitude are the Fourier transform of the image domain sky image. And you can observe the N0 and 1 and 2. As you go higher order, you will start seeing thinner ring and even dimmer rings. And if you translate that into a Fourier domain, you will see N1 dominating at the lower resolution or lower baseline length, which is how far each telescopes are, how far the furthest telescope in observations are. And if you go farther, higher baseline length, which is like around moon, between moon and Earth, you will start seeing N2 and 3 photon rings dominating in visibility amplitude domain. So this thin ring can be observed if you have a telescope between Earth and moon. And in the current EHD, resolution is just this much. What we are seeing will be all components from N1, 2, 3, and N0, which is the diffused image. So I will want to ask question, what can be done in Kerr-naked singularity, which is a super spinning black hole in Kerr space-time. If you have a parameter spin parameter over 1, which is the Kerr bound, you will start seeing naked singularities without event horizon. Unlike the black hole case, there's no event horizon, photon residual structure changes. It is expected that we started seeing the shadow region we started seeing the gap in the shadow region that is studied. And I'm going to be looking at images of those from the GLMHD simulation that came out last year. So this is the this is the first image that they took. They calculated comparing from black holes on the top panels and the negative singularities on the bottom. You can see this is the black hole shadow region, but in negative singularities case, you will start seeing the second ring appear in the nominal shadow region. So I went further analysis on these images and calculated the first image of Kerr negative singularity photon rings. This is the image of from our work at the spin 1.01, so just 1% above the Kerr bound. And this blue line is the shadow that we explored earlier that started showing the gap. And the interesting feature in this image is that we started seeing the emissions inside the nominal shadow region, and also those emissions are spread out and even thicker in the image domain. And also those shadow opening gap has been connected in the emission, and also have multiple layers of rings on both outside and inside of those blue lines. And then we can further decompose those into different order, depending on how many turns that they made before escaping. So at N0, you have double ring, and 1, you do have double ring, 1 outside the region, outside the curve, and 1 inside is even so thicker. And N2 also have a double ring. The outer ring you cannot almost see in the image domain. And also at the higher inclination angle with respect to the spin axis, you will start seeing those curves starting showing the gap. At N1, it was connected, but N2, you will start seeing the gap in the image. So the takeaway is that in Kerr negative singularity case, each order of photon rings form double rings. It's different from the one from black hole case. And also, gaps in the ring structure only appears in high order photon ring starting from N2, and also need sufficient higher inclination angle. I did decompose those into 1 ring outside and 1 ring inside to observe the VLBI signatures. If you have a thin ring, which is one outside of the curve, you will start seeing those components dominating at the higher baseline length. So if you observe at the higher baseline length, longer baseline length, you will start observing just this outer ring instead of both of those rings. And so in the visibility amplitude or Fourier domain, you will start seeing the thinner ring dominating on the higher baseline length, which is same as the black hole case, but those rings are both in 1 photon ring. So that's the differences there. And we will further ask questions. Can we even distinguish those in current EHD resolution? Left panels are the high resolution simulation, and on the right is the simulation data that is brought into EHD resolution to visually explore if it's even distinguishable or not. I will say this is not distinguishable and nice. We can see those 2 images looks pretty similar, and because of the double ring, you will have thicker bright part in the image domain, and then smaller smaller shadow region. But those can be within the domain of the exploration for the EHD, that we don't have a way to distinguish those until you go higher baseline length and resolve those small scale features in the future. And this is my summary. The horizonless spacetimes produce the measurable deviation and ring hierarchy. We started seeing the N1 forming double rings, and N2 rings also form a double ring, but N1 outside ring is so much thinner than N2 rings. Those deviations can appear in visibility amplitude directly. If you observe at different baseline length, you will see different features in the rings. So having a extended baseline length for the observation can lead us to different signatures in a smaller scale, so that we can clearly distinguish those negative singularity with the black hole. So thank you.
So Hina, I must be missing something really important, because in a black hole case, no light can escape from the inside of the event horizon. That's why it casts a shadow. That's why the event horizon is looking for a shadow, because no light can come from behind the black hole. The whole point about a naked singularity is that light can come out of it. That's the whole point about naked singularity. So why are we looking for a shadow at all? You know, there should be like a bright spot of light coming from the singularity. That would be the evidence for the singularity.
Well, the photon rings are going to, so even in the black hole case, you will...
No, I'm not talking about the black hole case. I'm talking about the naked singularity case. I'm saying light, the definition of a naked singularity is that light can come out of it from inside the event horizon of a black hole corresponding to the same thing. So the whole point about naked singularity is that light can escape from it. It's a source of light. Why do we care about the shadow?
Well, so the singularity is still a ring, and then
Why don't we see the singularity?
Well, singularity is something that we cannot observe, and singularity is the photon ring. So if you...
There shouldn't be a dark region because we can see through. The whole point of a naked singularity is we can see through all the way to the singularity. It's naked. We can see it. That's the definition of a naked singularity.
It's a fainter.
Why would it be fainter?
Well, the gravitation will allow.
No, are you sure?
Because you're looking at a specific frequency, so you still expect a redshift in that regime. You can imagine that the emission's getting like redshifted out.
But is it true that if you put a light bulb in the metric of a naked singularity, you won't be able to see it?
I would imagine at certain
Yeah,
frequencies.
Because of redshift?
I would think so.
It's a gravitational well.
So photons can, no, a gravitational well is the whole point about the black hole, that photons cannot escape. In a naked singularity, that's the definition. They should be able to escape.
You can see it, but it's fainter, so it's more difficult. Come thinner in the center. Of the same region.
Is it obvious? Because you should also get brighter because you're concentrating the social
Singularity is quite possible.
Yeah, so the question is what wins, right?
Yeah, which way?
Yeah, so are you saying that the singularity itself is always dark? If you do an accretion flow onto a naked singularity, the light emitted close to the singularity is not visible to us?
Light emitted at the singularity?
That's the whole question, because is it a shadow or is it a source of light?
A light emitted at the singularity, you cannot observe it.
Because, well, it's not necessarily just at the singularity. The entire region should be bright because you are seeing through it. You know, light can escape from a naked singularity metric.
There's also an aspect of the GMH3 simulation that shows that there's like a centrifugal barrier. So like the accretion doesn't actually go all the way to the singularity. So like the emission coming from the accretion is actually a little bit, just slightly further away. So it's still within 2 or 3, but there's still like a region where you don't have accretion going all the way.
Why is accretion blocked from going all the way?
That's what the simulation shows.
That's not an explanation. That's saying the computer gives me that is not an explanation.
There's a centrifugal barrier coming from the ring singularity.
Matter should be able to flow all the way to the center, just like in the case of the black hole. I don't see why matter would stop at some point. Yeah, so anyway, it's surprising to me at least that it's dark in the middle, that's all.
But aren't you seeing some of what you're saying in the geometry where if you have spin that's a little bit more than one, like there is a bright spot, and because of the curvature related to the spin, it's just a little bit off center. Does that,
Where is the bright
like, if you look, like there was the gap side and then the bright side of your diagrams? Isn't that representative of these same dynamics where you're seeing emission?
Gap side of, yeah, sorry. So to mention that this gap, we believe that we cut off the image calculation at the singularity. So we are looking at this is the numerical factor that we didn't resolve yet, but we are looking at the projection of a singularity in this gap.
Dark region is of the same size in both cases, right? Of the black hole and is it not?
It's not the same.
Are we seeing light from the region that for a black hole case we won't see light?
Yes.
Okay, can you show us?
Yeah, this. So you have two. You have two rings, and one outside. If you don't know if you can see it, the outside is something that you observe with the black hole, and then this thick ring inside is something that you don't observe in the black hole case. It's something that is inside of the black hole shadow. So if you look at this is very clear that so this ring in the middle, smaller ring, this is something you don't see in the black hole with the same configuration. So that second ring, smaller second ring, is something unique in the negative singularity.
Okay, very interesting. But there is no brightness at the center.
Yes, correct.
Okay, and questions and other comments? Very interesting. So then the next question is, does nature provide us with naked singularities? So far we haven't seen them. It will be bad news for general relativity, because then it means the entire universe cannot be predicted. Because if a naked singularity is a place where general relativity breaks down and it affects everything around it, it changes the history of the universe in ways that we cannot forecast.
Yeah,
it's a big problem to general relativity.
Yeah, sure. We don't know the formation of negative singularity, but it's still a solution of Einstein's equation.
Right,
so
but gladly we haven't seen it yet. If we see what you're describing, that would be a big problem to Einstein's theory of gravity.
Yeah, excitement.
So in your simulation, the light is coming from, by assumption, the accretion, right?
Yes.
Yeah, that's the reason. They don't assume there's a light from the center.
No. I was asking about the accretion. So the accretion goes all the way to the singularity. Why don't we see a brightness from there? That was my. So it may be the redshift. I'm not sure, but maybe it's the redshift. Yeah. Thank you so much.
Thank you.
Hello everyone, my name is Catherine Petretti. I am a fourth year PhD candidate here working with Xingang Chen, and I'll be talking about constraining dark matter isocurvature fluctuations with the CMB. So just starting off, what exactly is cold dark matter isocurvature? So typically when we talk about inflation, we're talking about it producing quantum fluctuations that are produced that get stretched out during the inflationary process. And these end up seeding the gravitational wells where matter and dark matter and radiation all flow into. So if we are looking at here, so this would be the total linear combination of all of the perturbations from inflation, and then if we look at just a single component of that, picking out the matter, say, we would see that the fluctuations perfectly line up in this case, and these are called adiabatic fluctuations. Now, isocurvature is a case where there's another source that's causing another fluctuation happening in one of the components of matter. So in this case, this would be happening in cold dark matter. So if we look at the total linear combination of all the fluctuations, and then we separate out just the dark matter fluctuations, we see that they would be out of phase with the rest of the fluctuations. So in the CMB, this would look like on, these are both the temperature power spectrum in the CMB. So I'll focus first on this left side. So we see that there is the adiabatic fluctuations produce the typical acoustic peaks in the temperature power spectrum. And then if we have an extreme, very high amplitude cold dark matter isocurvature case, which is this blue dashed line, we see that we're able to also get these acoustic peaks, but they would be shifted from the adiabatic perturbations. And then the right side here is just maybe a more realistic case where the black line is again the same power spectrum that's on the left, just the y-axis is scaled in a log scale now. And then this blue line is a different cold dark matter isocurvature fluctuation, and then the red dashed line would be the linear combination of both of them. So we'd be measuring the total red line here, and then from that measurement we'd be able to compare it to, say, the adiabatic case and see if there's any additional fluctuation there that could be contributed from CDI, from cold dark matter isocurvature. So in terms of how this is parameterized, so this is parameterized by the scalar power spectrum. So typically the curvature power spectrums from inflation are parameterized with this equation where you have the amplitude of the fluctuations and then the spectral index or the spectral tilt. So the scalar power spectrum for the adiabatic perturbations would be this gray dashed line here as measured by Planck, using the Planck parameters for the AS and NS. And then isocurvature perturbations would be parameterized in a very similar way, where this F iso squared is the fraction of the two amplitudes between the adiabatic power spectrum and the isocurvature power spectrum. And you can give different tilts here for N iso. So you can have a very red tilted spectrum where you have a lot of power on large scales if N iso is less than 1. If N iso is greater than 1, you can get a very blue tilted spectrum where you have a lot of power on small scales, or you can have a flat spectrum, which would be this black line. And then in the temperature power spectrum in the CMB, again, this gray dashed line is just the adiabatic contribution, and then all of these colored lines correspond to the different power spectra here. So we'd get more power on large scales for the red tilted spectra, or more power on small scales for the blue tilted spectra. So one way that these could be sourced is with if an axion would be present during inflation. So this is a quick recap of axions. So they're a very good dark matter candidate because they're very light, weakly interacting particles. They're originally proposed to solve the strong CP problem, where the QCD Lagrangian has some CP violation in it, but we don't detect CP violations, so the axion was proposed as a solution to that. So you would have this Petretti or PQ symmetry that is being broken. So when the symmetry is broken, the potential for the axion field takes on this Mexican hat shape, and then the axion can circle around the bottom of this potential minimum. So it would fall down into this potential well here. So if this symmetry were broken before or during inflation, you would have this axion that's present, and then due to quantum fluctuations, it can start to sort of wiggle around this potential minimum, and these quantum fluctuations would get stretched during inflation, and these would be independent of the other quantum fluctuations that would source the adiabatic perturbations. So the amplitudes of these perturbations are set by the inflationary scale, so the Hubble parameter during inflation, HI. And so this has two implications. One is that in this sort of minimal case, because the Hubble scale is constant during inflation, all of the amplitudes at all the scales would have the same amplitude, so you would expect to have a flat spectrum, so a spectral index of 1. But you would also, this also tells you that if you have constraints on the amplitude of the axion isocurvature, you can also have constraints on the inflationary energy scale, which is very important for if you're trying to detect, say, primordial gravitational waves that have a given energy scale that you need in order to detect them. So if you have constraints on, if we were to detect those, for example, that would rule out some of these isocurvature models. And you can have more complicated dynamics here, such as maybe coupling between the inflaton and the axion that would give you a red or blue tilted spectra or oscillatory features. But the main point here is that axion isocurvature could source dark matter isocurvature. If the axion is present during inflation and then becomes part of dark matter, then this would contribute to the cold dark matter isocurvature. So Planck and ACT do have some constraints on the dark matter isocurvature. So this is just showing the temperature, E-mode polarization, and the cross-correlation power spectra for Planck and ACT data. So Planck is the orange dots and ACT is the blue dots. The main thing here is that ACT data goes up to very, very small scales, up to multiples of 8,500. So here it's only showing up to 4,000, but this would be about 0.02 degrees on the sky. So very, very high resolution in ACT data, which means that if you have a blue tilted spectrum, it would be more constrained by ACT data than Planck data, which mainly constrains larger scales. Also, you can see that especially in the E-mode polarization, ACT has much smaller error bars than Planck data, and then also a little bit in temperature as well in these intermediate scales over here. So Planck and ACT do have reports for axion isocurvature constraints, or dark matter isocurvature constraints, I should say, for the flat case, NISO is 1, and also setting NISO as a free parameter. But the goal of the research that I'll be presenting on the next couple slides is to be able to extend this analysis to include larger range of NISOs, 0, 1, 2, and 3, in order to test these beyond minimal axion isocurvature scenarios, and also including the free isocurvature scenarios. And again, just a good reason to use ACT data for these very blue tilted spectra, where NISO is 2 and 3, is because it has much tighter constraints on these smaller scales. So for the fixed NISO cases, so these are showing the constraints on the power spectrum amplitude given at a particular scale. So this is showing it at a scale of K1 is 0.002 megaparsecs, or inverse megaparsecs. And so this is NISO 0, 1, 2, and 3 for Planck and Planck plus ACT data. So for the NISO 0 case, this would be a very red tilted spectrum. Because most of the power that you see is going to be at large scales, your mainly Planck is going to constrain this about the same as Planck plus ACT, so the results are very similar there. NISO 1 and NISO 2 are very interesting because you can see that Planck actually has a slightly better constraint on this amplitude than the PACT case. And so the reason for this is because, or one of the main reasons for this is because you do have larger power on these intermediate scales, but it's not on large enough scales where ACT data becomes more constraining than Planck. So you end up getting a better constraint just from Planck alone, and then ACT data doesn't really do much here. But then for the very extremely blue tilted case with NISOs 3, you get that the constraint ends up being very similar again. So for in a very extremely blue tilted case, ACT starts to become important. And then for the case of setting free NISO as a free parameter, so this is a triangle plot showing the results for these. So this is showing, again, the constraints on the power spectrum at the same scale, 0.02 inverse megaparsecs. This is showing the constraint on another power spectrum scale, so this would be at 0.1 inverse megaparsecs. This is basically showing the constraints of the power spectrum on a larger scale and a smaller scale. And then this is showing the constraint on NISO. So what's interesting here, the interpretation here is a little bit different from the previous slide. So in this case, focusing on the Planck plus ACT case, this would be the red contours. We see that the constraint on NISO, which is 2.0 plus or minus about 1.5, and the Planck case is 2.2 plus or minus 1.7. So the Planck plus ACT case gives you actually a slightly redder spectrum than Planck alone. And the reason for this is because since you have tighter constraints at very blue scales, you're essentially being constrained to a straight line. So if you kind of push down one side, the other side kind of has to come up. So you get a looser bound at larger scales, but a tighter bound on smaller scales and a slightly blue spectrum than for Planck data alone. So just to leave off with the summary slide, so Planck and ACT are able to give some good upper bounds for cold dark matter isocurvature, but ACT only really becomes important for extremely blue tilted spectra. And so just some ongoing work that I've been doing for this, so to further this analysis with SPT data and LSS surveys, and also to look for oscillatory features in axion isocurvature. So thank you.
So Catherine, the observers in the audience would be interested to know how, given your constraints, is there any effect on galaxy formation or not?
I haven't looked into that, so not that I know of.
If you were to add the component of isocurvature, would you make galaxies earlier or not?
Well, the main constraint here is like for adiabatic perturbations, that would be the main seeds of the gravitational wells that would grow over time. So the main thing is that you'd expect those to attract the matter that would grow galaxy formation, but it might affect, if you have a dark matter curvature, that might affect like some dark matter halo formation potentially. So perhaps you'd see something there, but I think in general it would look pretty much the same.
Into that, because now the Webb telescope shows evidence for early galaxies. So
Yeah.
if you can explain it with isocurvature, that would be interesting.
Yeah.
Okay. Any other comments, questions? No? Okay, let's thank Catherine again.
Sorry. I'm sorry. Okay. All right. Good afternoon, everyone. Thanks for inviting me to talk about our project. My name is Pranav Sanghavi. I'm a postdoc working with Liam Connor here at CFA. And I'll be talking about the Coherent All-Sky Monitor. It's a new radio telescope we're building in the Owens Valley in California. And just a disclaimer, this talk will mostly be about all the stuff that goes before all the plots with the curvy lines and fun results. So all the shenanigans we need to do to make it happen. This telescope is primarily dedicated to detecting fast radio bursts. We already learned about fast radio bursts from Adam. I'll quickly rush through it. They are brief, about a microsecond, a millisecond, very bright. They've been detected from 200 megahertz to all the way up to 6 gigahertz. Most of them happen just once. A good fraction of them repeat, and they're pretty ubiquitous. About 1,000 of them happen all over the sky every day. And the key thing about them is they are extragalactic, and it's encoded in this dispersive sweep, in this quantity called dispersion measure. And what are they? We're in the process of figuring what makes them. And there are a few very strong candidates, magnetars, things happening in old stellar populations, orbital systems, and cataclysmic events. I believe they are, I think a neutron star a burst coming from a neutron star being eaten by a black hole. I'm not, these are papers I've read. Yeah.
Star collapsing into a black hole, and you get magnetic reconnection events. There's no evidence for the evidence.
Yeah. Look, back when I started my PhD in 2016, there were more theories than there were FRBs, and thanks to Chime, we've exceeded that. Yes, hundreds. But the strong ones, like magnetars, for which we got a sort of a smoking gun evidence by finding a FRB-like analog from a burst from a magnetar, the SGR 1945, from our own galaxy, which was detected by both Chime and the STARE-2 project. So it proves that magnetars can produce coherent emissions like FRBs. Moving on to, we found an FRB from a goblet cluster, which implies FRBs can exist in ancient populations where magnetars shouldn't exist. And then we found a repeater, which repeats with a known periodicity of about 16 days, and which says some FRBs are governed by orbital dynamics like mechanisms. So we know from all of these FRBs, which happen to be from a local universe close to us, that we have an evidence that we have a lot of different progenitor channels for FRBs. What can we learn from them? We learned something from Adam's talk that we can measure the baryon fraction of gas between galaxies. The dispersion measure is the key in this in using FRBs as probes, where we can count every baryon along the line of sight between the FRB and us. Back in 2020, we had this paper where we used the dispersion measure from localized galaxies to find where to get a baryon census. And other things that we could use FRBs for is look for gravitational lensing because of their short durations. You could look for nanosecond to millisecond time delays. And you could course correlate with galaxy surveys, map large-scale structure, and a lot more cool stuff. Oh, sorry. Thank you. So just quickly talking about the dispersion measure and all that we can glean from it. As Adam alluded earlier, and I'll just quickly go through it, the dispersion measure has contributions from our own galaxy, our galaxy's halo, the circumgalactic medium, the intergalactic medium, and the FRB host galaxy. But if our FRB host galaxy was really close to us in our local universe, the contribution from the intergalactic medium is negligible, and this clean line of sight will help us constrain the properties of the circumgalactic medium and learn more about it. A case study for this is this FRB detected 50 megaparsecs from us. With just one single FRB, we were able to place an upper limit for Milky Way's halo mass. And this just proves that FRB is a powerful tool to weigh the stuff between us, and it's less sensitive to systematics. And as mentioned before, they are quite ubiquitous. They happen all over the sky all the time. And which means if we were to find more FRBs locally, we could learn more about the CGM. Having local universe FRBs helps with multi-messenger code detection, so when X-rays and gravitational waves could get weaker for cosmological FRBs. And nearby FRBs helps resolve the tiniest things like a globular cluster. That could be a source. That could be a source for an FRB. The local universe fast Fourier bursts offer a unique opportunity to gain insights into the circumgalactic medium. So how do we maximally study FRBs and the local universe using FRBs? Find more of them. That is what motivates us to build this new telescope. And assuming the FRBs are distributed in the Euclidean universe, which is pretty valid for really low redshifts, we have this rate scaling equation. And it's quite evident that if we were to have a telescope with a very wide field of view. We maximize the number of detections, and all we need to do is keep adding individual antenna elements. So given that we have a very nice telescope with very low noise receiver systems, we could maximize the number of FRBs that we could detect. And here comes CHASM to take the next step towards this endeavor. It's led by our PIs, Liam Connor here at the CFA and Vikram Ravi at Caltech. So with a core array of wide field antennas and a bunch of outriggers to localize all the sources, we could create a very strong case for local universe FRBs being excellent probes and be able to eventually figure them out. So we assembled a crack team between CFA and Caltech and other institutes, and we chose our location. Like I mentioned before, it is being built at the Owens Valley Radio Observatory. Our first phase will have 256 antennas in a core array in a rectangular layout. We will have several hundreds of degree squares of field of view. We have an FPGA-based F engine and a GPU-based X engine. And we'll be searching for 1,000 beams, 1,024 stationary beams for FRBs all over the sky. I hope to detect an FRB a week. And with outriggers, using the existing infrastructure at Owens Valley Radio Observatory, which piggybacking of the successes of DSA 110, we'll be having outrigger locations right where the DSA 110 outriggers are to help with our localizations. So why would CHASM be great for FRBs? Our design is based on simple PCB dipoles for antennas, so no cost of steel to scale. And it's quite modular enough to go from 256 or 258 elements to about more than 1,000 elements trivially using just the infrastructure available at Owens Valley Radio Observatory. Moving forward for more than 10,000 elements or so, we'll primarily be limited by the cost of computation, the logistical considerations like power and space, and the cost of, I say hardware, but it's mostly the cost of copper. So what have we been building and what we plan to build? We will have a rectangular grid of 6 antennas, rows of 6 antennas, or 43 rows of 6 antennas with very low noise receivers, and going through back-end electronic modules, finally being fed to an F engine. Our antenna has already been designed. It's a PCB-based antenna, sensitive to our frequency range from 375 megahertz to 500 megahertz. Our analog chain is already designed, and I'll be working on the next and hopefully the final iteration to give us a better noise characteristics. A digital backend follows a quite standard backend for radio telescopes. We have an F engine which analyzes the raw voltages. We have a packet capture system followed by a correlator beamformer, FRB search, and a classification notification system. The F engine is the SnapFAT platform developed by the Casper collaboration. Each F engine would sample 250 megasamples per second, all 12 inputs, and give us a 225 megahertz bandwidth. And each board will send over a 10 gigabit Ethernet link. 43 snap boards for CHASM 256 will give us a data rate of around 390 gigabit per second, which would be captured by a carrier grade switch, sending it over to a receiver node that would aggregate it into a ring buffer for downstream processing, like building a correlator and beamformer. The downstream processing is GPU based. We have 2 implementations of a beamformer which would form 1,000 stationary beams in the sky. One is a simple voltage summing delay summing beamformer based on NVIDIA Cutlass running on GPUs. For a full array, we have an FFT-based beamformer which uses a significantly small fraction of GPU resources. The FRB search is also implemented on GPUs, and which the FRB search basically de-disperses the pulse and uses a match filter to generate a bunch of candidates. Once we have all the candidates, we'll be greeted with a flood of false detections from RFI, and we have a pipeline and a plan for improvements for it to classify and notify us using machine learning tools. And where we are right now, CASM 256, we have we're well on our way with most of our RF procurement. As you can see, our ground screen is hardware cloth you could get from a hardware store, which is just a mesh of galvanized steel wires. Our radomes are plastic containers from the container store, and PVC pipes for stands. It's really interesting about radio astronomy and low frequencies where we could get away with a lot of low-tech equipment. This is some of our signal from the sky from one antenna. We do see evidence of human RFI from satellite downlinks and LTE signals as seen over here and here, which are aliased into our actual signal that are captured by our digitizer. To mitigate all of this, we are working on the second iteration of our analog chain, which will be commissioned later this year in the next few months. A big challenge for CASM would be RFI. And the RFI, in addition to terrestrial RFI, which seems to be quite clean at overall, we do have a very wide beam, and we are inundated by satellite constellations. At any given time, there are 30 in our beam and about 700 above the horizon, and so especially from Starlink and OneWeb, and it's only going worse. So this will be a challenge which we'll be tackling as we commission our telescope. We've had our first light as of this December. This past December, as you can see fringes from a 2-element interferometer. You can see bright sources like Cassia, Tau A, and the sun. We are slowly building our array, adding more and more elements as we move forward. Currently, we have 16 analog chains ready to go and capturing data and registering fringes. And yes, the dense aperture arrays like CASM are the future of fast radio bursts, where they could leverage the advantages that we have from Moore's law for now and be mass-produce a lot of antennas, a lot of digital chains, and be able to detect lots of FRBs. Our Pathfinder with CASM 256's OVROs will localize about 100 local universe FRBs per year. And CASM's now the only one looking for FRBs. Chime and Chord and DSA will be our peers, and we would be complementing them. And we also have Burst in Taiwan and Charts working on similar goals as us. A future CASM, once we prove our a Pathfinder array with 10,000 antennas, could find hundreds of thousands of FRBs per year. And as of now, we have a full digital pipeline primed for testing, and our analog chain is slowly being commissioned and hope to have full science operations at the end of the year.
Pranav, the breakthrough in this business of FRBs will come from another wavelength. If we detect an optical counterpart,
Indeed,
for
yes.
example. So is there any effort to work with sky surveys in the optical notice something at the same time that you're observing the sky?
Yes.
Any?
So Argus and Chasm have identical fields of view, and they're both in the southwestern U.S., so they're very complementary.
So they will operate at the same time?
Same time, same field of view. 20%.
Right, so that may be the breakthrough. Yeah, because we really need another wavelength to figure out the nature of these sources.
Indeed.
Yeah. Okay.
I can add to that Chime has VO events triggers with Swift and several ground-based telescopes as well.
But Swift is X-rays.
Yeah.
These photons are very precious. Not many of them, you know.
Yeah.
But the optical, there are more.
We had a brief moment where we thought we might have gotten coincident X-ray with RB float last year, and it didn't pan out, but.
Right, so it's the number of photons, yeah. But maybe optical or infrared would be helpful. Okay, well, we are over the time limit, so let's thank Pranav and all these people.